Today we continue our discussion on synthesis of cam profile for a flat face oscillating follower. Let the base circle of the cam be given and when the follower, flat face follower, is in contact with the base circle, that is the lowest position of the follower, and the oscillating follower is hinged at this location. This dimension we called E. The location of the follower hinge from the camshaft was given by these two dimensions A and B. The angle that the follower face makes with the horizontal as this lowest position we denoted by psi B. That is the angle E makes with the vertical or the follower face makes with the horizontal. In our last lecture, we got an expression for this psi B, which was base circle radius is RB, sine inverse RB plus E divided by the distance O2, O3, which is nothing but A square plus B square minus tan inverse B by A. Now, when the cam rotates from this position by an angle theta, let the follower rotates by an angle delta theta. The follower has rotated by an angle delta theta, and this is the follower face. So this is the cam surface, cam profile. We denote the distance of this contact point on the cam, let me call it C. This is the common normal between the cam profile and the follower surface, and let's say this distance is L, which keeps on changing as the cam rotates because the contact point shifts on this cam surface. As we have done for the translating follower situation, we take our x and y axis passing through O2. This is the x axis, this is y axis, this is the x axis. Our objective is to find the coordinates of the contact point, namely xc and yc. To find this xc and yc, I will need this quantity L. So as a first step, I try to find what is this quantity L. Towards that end, I drop a perpendicular from O2 to this common normal. From O2, I drop a perpendicular to this common normal and let this point I call M. The follower position is at this instant again measured from the horizontal is given by psi, and as we noted in our last class, psi is nothing but psi b plus delta theta. Psi b we have already got, delta theta is prescribed for us, so I can find psi. To find this distance L, we consider a point C1 on the follower surface, but at this instant coincident with C. C belongs to the point on the cam and C1 denotes the point on the follower surface which are in contact. To maintain the contact, velocity of this point C1 and this point C along the direction of NN must be same. Otherwise the contact will be either lost or one point will get into the other point. That means because they are rigid body, that cannot happen. To maintain the contact, velocity of the point C1 along the direction NN must be velocity of the point C along the same direction. Now, because M and C are 2 points on the cam which is a rigid body, so velocity of C and M along the line CM, that is along NN, must be same. So, VC NN is nothing but velocity of this point M in the NN direction. Because there are 2 points on the same rigid body, so this distance CM does not change. That means their velocity along this direction must be same. And velocity of C and CN and C1 along NN must be same, otherwise the contact will be lost. Now, to find the velocity of the point M along NN is nothing but O2m into the angular velocity of the cam. So, this I can write is O2m into angular velocity of the cam d theta dt, and that is velocity is in this direction. If omega d theta dt is counterclockwise, velocity of m is along NN and O2m into d theta dt. Now, velocity of C1 along NN is nothing but L times psi dot. So, the Vc1, the velocity of the point C1 along NN, where N1 belongs to the follower surface, is nothing but L into d psi dt, where psi is measured clockwise. And because these two are same, I can immediately write O2m is nothing but L into d psi d theta. Once I get this O2m equal to L into d psi d theta, then I can write, as I see, if this angle from the horizontal is psi and this line is perpendicular to this line is also perpendicular to this line, so these two lines are parallel, so this angle is also psi. So, I can write O2m is A cos psi minus B sin psi. E is perpendicular to M, so there is no component, and then minus L. O2m is, I am going from O2 to M in this way, O2 to this point, to this point, to this point, to this point, and this point. So, O2m, if I add up these vectors, the components if I take, A will give me cos psi, B will give me minus B sin psi, E will not give anything, L will again give L cos psi, but is a negative sign. L will give again L, but in this direction, so minus L. And O2m is L psi prime. So, this is A cos psi minus B sin psi minus L. So, that gives me L equal to A cos psi minus B sin psi divided by 1 plus psi prime. So I get this quantity L, this distance L, which changes with theta because psi is a function of theta. Now we are in a position to write the coordinate of xc is A minus this angle is psi, so E sin psi minus L cos psi. X coordinate of this point C is A. There is no projection of B on the horizontal direction. Horizontal position of E is E sin psi, but in this direction projection of L is L cos psi, and in this direction, so that is the coordinate xc. Similarly, we can write yc is B minus E cos psi plus L sin. Out of which L I get from this expression. So I have got xc and yc everything in terms of theta once these parameters A, B, E are given to us. Rest is as before. Once I get the contact point, I can write Rc is square root of xc squared plus yc squared. As we see, this is a function of theta. And from any line fixed on the cam, any line which I fix on the cam, then if I measure the polar angle from here, if I call it say some alpha c prime, then alpha c prime is theta plus tan inverse xc by yc. So this is also a function of theta. So this is the parametric equation of the cam profile in polar coordinates with the origin here. Rc, which we can get for various values of theta, alpha c prime, which I can again get for various values of theta, but theta represents the cam rotation. So varying theta from 0 to 2 pi, I can get Rc and alpha c for various values of theta. Then plotting those values of Rc and alpha c prime, I get the cam profile, as we have done in case of translating followers. This portion is exactly as before. One point I would like to emphasize at this stage, that once we get the Rc, that the distance from the camshaft axis, and the polar angle for the contact point, for all types of follower, translating or oscillating does not matter. If I summarize this method of analytical method for synthesis of cam profile, we are getting Rc as a function of cam rotation and a polar angle, which I denoted by phi c prime or psi c prime or alpha c prime in various cases. Let me write one of them. I just call theta c prime, which is theta plus tan inverse xc by yc, and this Rc is nothing but square root of xc squared plus yc squared. So these two quantities I can calculate for all values of theta. And now to draw the cam profile after getting this series of values, what I can decide that I will draw the cam profile when the cam has rotated, say by an angle theta 0. So what I do, I take an origin which is O2, draw a line which is vertical, then draw a line at an angle theta 0. Then take these values of Rc and theta c prime, but theta c prime I measure in the clockwise direction from this line. So say for some values of theta I get Rc and theta c prime this point, then this point, then this point, like that, and joining these points I will get the cam profile when the cam has rotated by an angle theta 0. So, this is where we end our discussion on analytical method of cam profile synthesis. Next we will do how to do it, the same thing, synthesis of cam profile for various types of follower by graphical method. Now that we have finished discussion on the analytical method of cam profile synthesis, we will do the same problem through graphical method. Graphical method of cam profile synthesis. Of course, we assume all the geometrical parameters like base circle radius, offsets, all these quantities are known, and only thing, instead of y, the follower movement being given in the form of an analytical expression, now we have it in the form of a displacement diagram. It is given in the form of a displacement diagram. Now, given the displacement diagram, how can you obtain the cam profile through a graphical method? So, as before, we start with translating follower. First, we discuss if the follower is flat face type, or then we will discuss if the follower is a roller follower. So, what we do? We first draw the base circle. This is the camshaft. The offset is also given. So, let this be the follower axis, and this is the follower face at the lowest position. This is the offset. In the graphical method, this total rotation of theta from 0 to 2 pi we divide in certain number of station points. So, this is the 0, then we take various values of theta like theta 1, theta 2, theta 3, theta 4. These are called station points 0, 1, 2, 3, 4. How many divisions we take is the question, but obviously more number of points we take, more accurate will be our drawing. But obviously we cannot take too many points because then it will be very time consuming. So, I will just illustrate by taking 2, 3 station points and rest will be same. It can be easily followed. This is the follower axis. This line represents the follower axis. Obviously, this is corresponds to station point 0 when the follower is at its lowest position. Now, we draw the displacement diagram at the same level. Whatever is the displacement diagram, I draw it at the same level. Now, say this is the station point 1, this is station point 2. So, what we do? We project these points onto this line on the follower axis. Let us say this is 1, this is 2. So, here again I mark this as 1, this as 2. obtain the follower cam profile, as we have done in case of analytical method, we hold the cam fixed and make a kinematic inversion such that this fixed link rotate in the opposite direction. Suppose this is the rotation of the cam for station point 1, the cam rotation is theta 1 in the counterclockwise direction. So, the follower axis has to rotate for the same station point. The kinematic inversion is that the follower axis must rotate by same value of theta 1, but in the clockwise direction. So, if I draw a circle with radius E, then this I make theta 1 and draw a tangent. So, this follower axis have rotated by theta 1 in the clockwise direction corresponding to this station point. That is the kinematic inversion, that I hold the cam fixed and allow the follower axis or the fixed link to rotate by the same amount, but in the opposite direction. Now, the distance of this point corresponding to station point 1 from O2 is here. So, this is the distance. But now, this line represents the follower axis at this distance. So, I rotate this radius along this circular arc and intersect here. So, this is what I call, give it a name, say 1 prime. And the follower, this is the follower axis. So, the follower face is perpendicular to that, but at this distance. So, I draw a line perpendicular to the follower axis. So, this line represents the follower face after kinematic inversion corresponding to station point 1. Similarly, corresponding to station point 2, I rotate it by theta 2 . And this particular point of the follower axis should be at this location, that is so much distance from O2. So, I rotate O2 and this is what I call 2 prime. Then the follower face is perpendicular to this line. So, this is the follower face corresponding to station point 2. This way I can draw the inverted position of the follower face corresponding to all the station points 1, 2, 3 and so on. And the cam profile is nothing but a curve which is an envelope to this family of straight line representing the follower faces. I draw an envelope to these straight lines which represents the follower face after kinematic inversion, and then draw an envelope to this family of straight lines, and that is nothing but the cam profile. So, this is the cam profile which is always tangent to the follower face, and these lines represents the follower faces corresponding to station point 1 and 2. And the same construction can be continued for all the station points, and we have to draw a curve which is tangent to this family of straight line representing the follower face. So, the basic thing is the kinematic inversion. The kinematic inversion is simple, as if we to draw these lines, we draw tangent to this circle which is called, in some book it is mentioned as offset circle, which is a circle of radius E with center at O2. But simplest thing is to rotate this line O2A1 by an angle theta 1, then O2 by an angle theta 2. It is very easy to show from the triangle law that this distance is same as this distance, because both of them are E. Then this distance this distance, if I consider station point 1, this distance is same as this distance. So this particular right angle triangle is same as this right angle triangle. So this whole right angle triangle has been rotated by an angle theta 1 in the clockwise direction. So I can just as well say O2A1 rotated by theta 1, I get this point. O22 rotated by theta 2, I get this point. And once I get this point, then I can draw the follower face perpendicular to the follower axis. Next, I will take up a roller follower, but translating. Let me now explain the graphical method for a translating roller follower. For the roller follower, first let me draw the prime circle. This is the cam center, O2, and this is the prime circle. So the radius is RP, which is RB plus RR. And let's say the offset is E. This is the offset E. So this is, as we have discussed in case of analytical method, this is the lowest point of the roller center, that is the trace point. The displacement of the follower will be measured from this level. So I draw a horizontal line and draw whatever is the displacement diagram here. So as before, I consider say few station points, namely 1, 2, 3. This is the plot of y versus theta. This is 0. So now I know that corresponding to the station point 1, the trace point should be here. Similarly, for the station point 3, the trace point should be here, and for 2, the station point is here. So to get the inverted position of the station points, we know this offset means the cam is rotating in the counterclockwise direction. Corresponding to station point 1, the cam rotation is known, which is theta 1. So I get the inverted positions of this trace point corresponding to 1 by rotating O2A1 through an angle theta 1, but in the clockwise direction. So if I rotate this by theta 1, this I call inverted position of the station point 1, which is 1 prime. Similarly, for this 2, I rotate about O2, this line O22 through an angle theta 2 in the clockwise direction through theta 2, and I get the inverted position of this trace point as 2 prime. Similarly, I do for all the station points, namely 1, 2, 3, 4, like that. These are the inverted position of the trace point. What is the trace point? Trace point is the roller center, and the roller radius is given. So everywhere this is the corresponding to 0, this is 0, so I draw the roller whose radius is given. Here again, this is the inverted. With this point as center, I draw the roller. With this point as center, I draw the same roller. So this way I keep on drawing roller. This is the, say, 3 prime, the inverted position of this trace point corresponding to third station point. Now, what is the cam profile? Cam profile is nothing but the family of curve. Cam profile is nothing but the curve which is enveloped to this family of circles representing the roller after kinematic inversion. So, I have to draw a curve which is tangent to this series of circles. If I draw a curve which is tangent to all these circles, that will give me the cam profile. So, the methodology is just the same as analytical method. I make a kinematic inversion with the cam fixed, get the inverted position corresponding to the trace point, draw the family of straight lines or circles representing the flat face or the roller follower. Then the cam profile is nothing but the envelope to this family of circles in case of roller followers, or in case of flat face follower to the family of straight lines representing the follower face at the inverted positions. So, this principle of kinematic inversion is very important, that you hold the cam fixed and allow the fixed link to rotate in the opposite direction. The cam is rotating in the counterclockwise direction. So, this follower axis for translating roller follower is rotated in the clockwise direction. That rotation can be done very easily geometrically by rotating this line O2A1, O2-2, O2-3 by theta 1, theta 2, theta 3 in the clockwise direction. That gives me the location of this trace point of the roller centers. Once I get the roller centers, I can draw the rollers, and cam profile is enveloped to this family of circles representing the roller face. In fact, if you can imagine, I can draw another envelope touching the circles on the outer side. This was touching the circles on the inner side. Then I can use this as the groove in the cam face where I do not need a spring. As I told you earlier, that without the spring for returning the follower, I can use a groove in the cam face of the cam and put the roller in that groove, and then cam will always push it up and pull it down. There is no need to have a spring. Actually, this curve is nothing but what we call prime curve, pitch curve. This is what we call pitch curve. So, this is the cam profile if we have a spring, and this groove is the groove where I have to put the roller when I do not need to use the spring using a roller follower. Next, we will show how to use the same principle to obtain the cam profile for an oscillating follower, either roller or flat face. Let me now explain the graphical method of cam profile synthesis with reference to an oscillating follower. Here again we shall discuss both roller follower and flat face follower. So, first let me take a roller follower. Of course, we assume all the required geometric dimensions like RB, RR, all these things are already known, and the displacement function or displacement diagram is given to us. So, for the roller follower, let me first draw the prime circle. This is the prime circle radius, which is, as we have noted earlier, base circle radius plus roller radius. When the roller center or the trace point is in contact with the prime circle, that is the extreme position or the lowest position of the follower from where we measure the movement of the follower. This point we called O2. Suppose this is the roller center at the lowest most position. This is the and this roller follower is say hinged here to the fixed link. This point we called O3. When the cam rotates in the counterclockwise direction, let us say this follower also goes in the counterclockwise direction, and this rotation psi as a function of theta is known. So, the trace point will obviously go on this circle with radius center at O3 and this as radius. This will move on this circle. So, if we take station points corresponding to theta 1, theta 2, theta 3, then we will know the corresponding values of psi, theta 1, psi, theta 2 and so on. So, corresponding to station point 1, let us say the trace point is here. That means this rotation of the follower is psi theta 1. Similarly, I can get all the station points corresponding, all the trace points corresponding to station point 1, station point 2 and so on. Now, as before, we make a kinematic inversion. To draw the cam profile, we hold the cam fixed, which means this fixed link O2, O3 has to rotate in the clockwise direction. So, corresponding to station point 1, the inverted position of O3 this is the circle with O2 as center and O2, O3 as radius, and after the inversion, kinematic inversion with the cam fixed, this O3 will go on this circle. So, the corresponding to station point 1, when the cam has rotated theta 1 in the counterclockwise direction, this fixed link will rotate in the clockwise direction by an angle theta 1. So, this I can say O3 corresponding to 1 and the inverted position. Now, the distance of the trace point from this hinge does not change. So, distance of O3 1 should be same as O3 prime 1 prime, and the distance of 1 from O2 must be such that this required or desired follower movement is reproduced. So, what I do to get the inverted position of 1, I draw a circular arc with O2 as center and O2 1 as radius, and from O3 1 prime I draw a circle with O3 1 as radius. So, and where these two circles intersect, that is nothing but the station point inverted position corresponding to station point 1, that is the roller center. So, at this point I can again draw the roller whose radius is given to us. Let me again illustrate it, which corresponds to station point 2. We draw a circle with O2 as center and O2 2 as radius. 2 prime will lie on this circle, and O3 2 prime the inverted position of O3 corresponding to station point 2 is here on this circle, such that this angle is theta 2. Now, O32 is so much. So, from O32 prime I take the same radius as O32 and draw a circular arc. So, that let it be here. O3, 2. O3, 2. This distance is same as O3, 2 prime, 2 prime. This distance is same as this distance, and O2, 2 is same as O2, 2 prime. So this is the inverted position of the trace point, that is the roller center. So here again I draw the roller of same radius. And now if I draw a curve which is tangent to this family of circles, that gives me the cam profile. In fact, very simple geometrical consideration can show that this point we called 1 prime, that 1 prime I can easily get if I rotate O2 A1, O2 1 in the clockwise direction by theta 1, I get to 1 prime. Similarly, if I rotate O2 2 through an angle theta 2 in the clockwise direction, I get to 2 prime. This can be very easily proved from congruence of triangles, two equal triangles. You consider a triangle O2, O3, O1 and O3, 1, 1 prime, O2. You can show that very simply. This I leave for you to do, that instead of going through this by drawing two circular arcs, I can as well rotate O2 1 by theta 1 in the clockwise direction to get 1 prime, O2 2 by theta 2 in the clockwise direction to get 2 prime, and then draw the rollers and then draw an envelope to this family of circles. This I did to explain the kinematic inversion. It is actually this fixed link which is rotating. That means O3 is going along this circle in the clockwise direction when I hold the cam fixed. But from congruence of triangle, geometric construction can be much simplified by just not doing all this, only rotating O2 1 through this theta 1 and O2 2 through theta 2. Next, we will take up the case of a flat face follower. So at the end, let me now explain this graphical method for an oscillating follower which is flat face type. So if it is a flat face follower, let us say this is the base circle radius, and the flat face is tangential to this base circle radius at the lowest point, and this is where the follower is hinged. In the analytical method, this dimension is what we called E. As we see, as this thing rotates, this angle, this is one rigid body, this angle always remains 90 degree, which means the flat face is always perpendicular to this line. Let me use this particular contact point as the trace point, and as the cam rotates in the counterclockwise direction, as the follower oscillates in the counterclockwise direction, this particular trace point of the follower moves on a circle with O3 as center, this as radius and O3 as center. This trace point moves on this circle, and where will it be? Will be decided by the rotation of this this is what we call O2. So once this is prescribed, the movement of the follower. Again I consider station points theta 1, theta 2, theta 3, so on. This situation is shown for theta equal to 0. This is the situation when theta is 0. Let for theta, when it is theta 1, the cam has rotated by theta 1, this stress point goes here. So I call it as before 1. Similarly for 2, it comes here at 2. To draw the cam profile, I make use of the same principle of kinematic inversion, holding the cam fixed. So as explained earlier, for the roller follower, the inverted position of 1 can be easily obtained by rotating O2 1 through an angle theta 1 in the clockwise direction, because this O2 O3 moves in the clockwise direction. So this is what we call 1 prime. The next question is, how do I draw the flat face passing through this point 1 point, this flat face in the inverted position? For that, O2 O3 I rotate as before. The O3 inverted position is, say, here, which I call O3 1 prime. Now here I draw a circle of radius E with this point as center. This is of radius E, and the trace point is here, and I know the follower face will be always perpendicular to this offset E, which means this will be tangential to this circle. The offset E is same, and from 1 prime I draw a tangent So this represents the follower face after kinematic inversion. Similarly, I can rotate O2 2 through an angle theta 2 to get the inverted position 2 prime. Then I go to O3 2, wherever that is, by rotating O2 O3 through theta 2 in the clockwise direction. Then again I draw this circle of radius E, and from 2 prime I draw a tangent to that circle, and then that tangent, I am not drawing everything, it becomes cumbersome. Procedure is same. I go from 2 to 2 prime by rotating O2 2 through an angle theta 2 in the clockwise direction. That gives me this point. I rotate O2 O3 through theta 2 in the clockwise direction. That gives me O3 2 prime. Then with this point as center and of E radius, I draw a circle. From this point I draw a tangent to that circle, and that tangent, let it be this, that represents the inverted follower face. Now a curve which is tangent to all these inverted positions of the follower face and envelope to these inverted positions of the follower face. This is corresponding to 1, this is corresponding to 2, this is corresponding to 0. So once I get the inverted positions of the follower faces, which is a family of straight lines, then draw an envelope to this family of straight lines, that is nothing but the cam profile. What we should note, that here the contact point is 1, but here the contact point is not 1 prime, the contact point has shifted on the follower face, as we have seen in case of while we discuss the analytical method. Similarly, this is the 2' inverted position, but the contact point is here. So, if we measure what is the maximum distance of the contact point from the stress point on this side, that will give me the required follower width on the right hand direction. To the right of this contact point, how much the contact point moves, so that I must have the required follower phase. Similarly, if you continue, you will see now it will be to the left of this also. Right now it is to the right. For these 3 positions, 0 it is all right, 1 it is here, but the contact point is here, 2 the point is here, but the contact point is here. So, this is the shift of the contact point on the follower face in position 2. If you complete it, you will see that this contact point shifts in one direction, then returns and then shifts in the other direction, and the maximum distance that is needed for the contact point to move on the follower face, that decides the minimum follower face width, minimum width of the follower face. So, that brings us to the end of cam follower mechanisms, and let me summarize what we did. We first explained the different terms which are needed to describe the cam follower mechanism. After that, we described what are the typical follower movements, basic follower movements. We had both the analytical expressions and the graphical construction for the displacement diagram. Follower motion either y expressed as a function of theta or through displacement diagram. Then we showed how to get the basic dimensions like RB, E, etc., so that certain constants like minimum radius of curvature or maximum value of the pressure angle, all these conditions are satisfied. We would always obviously like to go for the smallest value of RB that we can get away with, so that the cam size is small. And after getting these basic dimensions, we discussed both the analytical and graphical methods to obtain the cam curve or the cam profile, and that is the synthesis problem. Of course, given the cam curve, we can also find what should be the follower movement, that is what we call analysis of the follower movement. But that is a purely geometrical problem which is quite simple, even you can do analytically or graphically, and we are not going to discuss that in this course.